Hi all and welcome to Biomolecules Revision. So the aim of this session is to A, go through the theory of biomolecules again, and B, answer some VCAR questions on biomolecules. So we'll start off by stating that there are four types of biomolecules. Bio meaning living, and molecules, well, you know what molecules mean. But it's not like the molecules are living. They refer to molecules found in living things. Okay? And there are four types of biomolecules. There are lipids, or we know them as fats, proteins, carbohydrates, and nucleic acids. Okay, so there are four types that we need to go over. So first we're going to start just on lipids. Might was great. So I don't draw on my table. Okay, so starting off with lipids. So the things that you need to know about lipids are the following. You need to know that lipids are fats, and you need to know about triglycerides and their formation. From the word triglycerides, we know that there's three of something, and glyceride comes from the word glycerol. It doesn't mean we have three glycerols. We actually have one glycerol. Glycerol can be found in your data book, and it looks like so. Now, if they ask for the systematic name of glycerol, you will simply say the IUPAC. So whenever they say systematic, this means IUPAC. So you count the number of carbons. There are 3, so it's prop. You look at the highest priority functional group, which is an ol. And then there are actually 3, so it's actually a triol. Oops. Let's try that again. There's no double bond, so it's a propane. And we have to number their position. So 1, 2, 3. Propane, 1, 2, 3, triol. And I will grab my data book as well. Just want to show you where glycerol is found in the data book so you know you don't have to remember it. Here we go, it's there. So fats are made out of a glycerol, systematic name propane 1, 2, 3 triol, and they're made out of 3 of something. Now these 3 of something are called fatty acids. Now fatty acids are also in your data book. They're here in this table. Fatty acids range from lauric acid all the way to arachidonic, and basically they differ in the number of carbons and the number of hydrogens, but they all have a carboxyl group. So fatty acids have a carboxyl group, and then they have an R group of a various form. Now we need 3 of these. Now if you have a look at the functional groups, we've got here being a hydroxyl and here being a carboxyl. When they react, they make an ester, and that's exactly what fats are. Hydroxyl plus carboxyl produces ester. plus H2O. It is known as a condensation reaction / esterification. And it is a 1 glycerol to 3 fatty acids ratio. Okay, so just showing the formation, I'm not going to dwell on this. You can fast forward this at any time if you're getting bored with me drawing it out, or you can try to pause it and draw it out yourself. Okay, so we know that we get the loss of water. That's why I want you to draw it out, because a lot of you forget what the linkage will look like. But if you know that you lose H2O, you can never go wrong. And 3H2O. So the ratio is a 1 glycerol to 3 fatty acids to 1 triglyceride to 3 waters. If we say that again, glycerol, fatty acids. Now your fatty acids could be all the same. They could be 2 different and 1 the same. They could be 2 the same and 1 different, or they could be all 3 different. It doesn't matter. Here we've got our triglyceride. This is our fat or our lipid. The fatty acid is not our fat. Okay, this guy is. This guy is the big nonpolar fat. It has 3 times ester linkages, which hold the components together. And we know that this is water. Now, if we go to what's polar and what's non-polar, something that VCAR may well ask, glycerol is definitely polar. Okay, it has OHs, which can undergo hydrogen bonding with other molecules, polar molecules, which have the potential to undergo hydrogen bonding. Fatty acids have a polar head where their carboxyl is, and a non-polar tail where the hydrocarbon is. Then we've got triglycerides. Now triglycerides are non-polar. They've lost their OH groups, okay, and they've formed ester groups, which are largely non-polar along with that. The ester group itself is slightly polar here at the C double bond O, but because they've got the long hydrocarbon chain, they've lost their OH, so they've become non-polar overall. But water itself is polar. Okay, we know that. So, another thing you need to know about fats is that they are made of fatty acids, which can be either saturated or unsaturated. Now what this means is that they can have only single bonds. That means max number of H. Or they can have at least one double bond, meaning that it's not the maximum number of H's. Now, how do we tell? Well, let's have a look at ethane. Actually, propane I've drawn. Now, propane looks like this. Its general formula, we know, being an alkane, is CnH2n plus 2. Now, let's say that we keep the same stem of propane, but let's turn it into a fatty acid, okay, which is essentially a carboxylic acid. Now, to make life easier, I know that we could just add a double bond O and an OH here, but I'm representing it in the same way that VCAR does with the COOH separate. So what we've done is we've gained a COOH. So if we're trying to write out the general formula, we've gained a COOH and we've lost a H. See, we've removed a H and we've replaced it with a COOH. So for a saturated fatty acid, it's CnH2n plus 1 COOH. And we know that if we want to turn it into something that's unsaturated, we could add a double bond. We'd have to remove 2 H's though. So the rule is, if it looks like that, it's saturated, but remove 2 H atoms per double bond. Okay, so let's have a look at some examples in our data book. Okay, that's not too bad. So, we've got this C11. Now just going by that C11, I'm going to work out what it is for a saturated fatty acid. So, C11, so that means N equals 11. That means 2 times 11 plus 1 should be the number of H's if it was saturated. So C11, 2 times 11 is 22, plus 1 is 23. Therefore, lauric acid is saturated. It fits that formula. There are no double bonds. Let's have a look at stearic acid. C17. Now 17 times 2 is 34, plus 1 is 35, COOH. Stearic acid is also saturated. Now let's have a look at linolenic acid. C17H35, COOH. Oops, it doesn't fit that formula. How many H's have we removed? From 35 to 29. 35 minus 29 is 6. Therefore, we've removed 6 H atoms. Now, if we remove 6 H atoms, we've removed 3. We've added 3 double bonds. So you call this guy unsaturated, 3 double bonds, and you would say that it is polyunsaturated. Polyunsaturated means more than 1 double bond. Okay? Now VCAR, of course, may give it to you in another way. They may say C20H32O2. There's nothing stopping them from giving it to you in the molecular formula. Okay? But what you need to do is simply put this into the CnH2n plus 1 COOH form, and you'll be fine. So what we do to put it in that form is we have our COOH. Now, of course, when we add that, we've removed our oxygens, we've removed one hydrogen, and we've removed one carbon. So it becomes C19H31 COOH. Now, C19H19 times 2 is 38 plus 1 is 39 COOH. Oh, it's unsaturated. 39 minus 31 is 8. Therefore, we have 4 double bonds. It's polyunsaturated, and it has 4 double bonds. Okay. Now, we also have to determine the property of fats made from saturated versus unsaturated fatty acids. So those that are saturated versus unsaturated. You may want to ask yourself which one is most likely a liquid at room temp, and which one's most likely a solid at room temp. You may want to pause it and ask yourself that, but not only that, ask yourself why. Okay, so when you are saturated, you have only single bonds. So we'll represent that here. But we know, in fact, it's not linear in arrangement. It's tetrahedral around each carbon. Each carbon adopts the same shape. If we are to draw this, so really, it's like this. You know how tetrahedral looks like that? It's more like this. 1, 2, 3. Oops, sorry. Don't know what happened with that last one. But anyway, it's more like that. Now, if we're drawing it skeletally, it looks like this. Remember, we only draw the carbon-to-carbon bonds. So if you've got two saturated fats which go together, they can pack together quite nicely. But if you've got something which is unsaturated, USAT, we get a double bond. And of course now, instead of being tetrahedral, it has 3 regions of negative space, so it needs to be triangular planar, or planar triangle. So it adopts a different shape around the double bond. But the rest of it is tetrahedral. So when you have a double bond, it creates what's known as a kink in the chain. Therefore, they are unable to pack as close together. And because dispersion forces only occur over short distances, those that are unsaturated have smaller dispersion forces and therefore a lower melting point. Therefore, if you said that unsaturated fats are most likely to be liquids at room temp, and saturated fats are most likely to be solids at room temp, you got it right. Okay. The next one is carbohydrates. Sorry about that. So for carbohydrates, it's very, very brief. Carbohydrates are not bonded together by ester linkages like in fats. They're bonded together with ether linkages, which, if you remember the ether bunny, it is like so. Whoops, like that. Okay, so another difference with carbohydrates and with proteins and with nucleic acids is that they are called polymers, which mean that they can be, they can be formed into polymers, which means that they are made or can be made of multiple monomers. So the monomer is a single unit, single molecule, which can react together to form polymers. Okay. So, in carbohydrates, the monomers are called monosaccharides. And we have learnt about a few of these monosaccharides. We've learnt about glucose, we've learnt about fructose, and we've just mentioned galactose. These are examples of the monomers, the building blocks. Okay, so so if we want to look at the sugar represented in our data book, well, there's two sugars. There's the one on deoxyribose and there's sucrose. Sucrose is what's known as a disaccharide. So monosaccharides have, monosaccharides are just one unit, whereas disaccharides are two units joined together. Okay, so here we've got sucrose. Now you need to know that sucrose has an ether linkage here and it's made up of glucose and fructose. You need to know that a lot of the functional groups make it very polar. It has a lot of OHs which can all undergo hydrogen bonding, making it very polar and very soluble in water. Okay, then you've got this ether link. Okay, then we have polysaccharides. Now we only went into polysaccharides, so polysaccharides is the polymer. And the way we draw the polymer is with open-ended bonds. Okay, so the polysaccharides that we went through are, so they are made of glucose monomers. So we learned about glycogen, starch, and cellulose. The main thing is just knowing the difference about them structurally. So while glycogen has, like if you just have a look, it's kind of represented pictorial here. So they're all made of glucose monomers, which is it's a 6-membered ring. It's not 6 carbons in the ring. It's got 5 carbons in the ring and 1 carbon outside of the ring. Now, the way it's orientated is in glycogen, they all have their carbons pointing in the same direction. And it's pictorially represented here. But in cellulose, it's got the carbons, the little branch coming off, in alternating directions. So up and down and up and down. And that's represented over here. Now starch is represented with all the carbons in the same direction, just like glycogen. These two have a very similar structure. It's just that glycogen tends to be more branched than starch. And that's really all you need to know about carbohydrates. Okay, we're going to go into proteins now. Proteins, there is quite a bit more that you need to know. So first of all, you need to know the monomer of proteins. We said that proteins can be turned into polymers. So the monomer is an amino acid. It is made up of a carboxyl group, an amino group, usually a H, and a Z group, which is alternating. All of your amino acids are in the data book. They've got all of them that are found in humans. Okay, show you where they are. Here we go. So we've got alanine, arginine, blah blah blah. They're all in alphabetical order. Here it's represented with the carboxyl group here, the amino group here, CH, and then the Z group. I'll show you an example where it doesn't have a H. Where's proline? In proline, it's actually got the amino group is connected to the Z group. It's very strange. Proline's a bit odd. But other than that, they all have that typical structure. Now, when 2 amino acids bond together, you have to know the type of reaction that occurs, and you need to know what link holds them together. So, it's an amino group reacting with a carboxyl group. So, we'll go like this, and we'll do glycine with alanine. Okay, you get the loss of water. A lot of people in the chem exam still have the oxygen between the N and the C. It's lost when you lose water. So it gives you this bond. And this bond is called the amide bond. You may see it called peptide bond, but you can only call it a peptide bond if it's between amino acids. So I just stick with amide. Another thing you need to know about amino acids is their acidic and basic properties. The first thing you have to know is that the NH2 group is a basic group. It can accept a H. And you need to know that the COOH group is an acidic group which can donate a H, okay, to become the conjugate base. So any of these amino acids are acidic and basic. So if it asks a question, what amino acid will react with HCl? The answer is any of them, as long as they've got a freed up, so they're a single amino acid, they've got a freed up amino group and carboxyl group. So when you're comparing the properties of amino acids, because they're the same in the amino and carboxyl group, you need to compare the Z groups. So you look at things like this. This is non-polar. Alanine's Z group is non-polar. It'll undergo dispersion force interactions. SH, cysteine as an amino acid is polar. It has an SH which can undergo dipole-dipole bonding. Glycine is non-polar, it just has a H. Here we've got serine polar. Here we've got other types of properties such as here we've got lysine. Lysine has an NH2 group. Its Z group is basic. Here we've got aspartic acid. Its Z group is acidic. Okay, so you've got to be careful about the properties as well. You've also got to know how amino acids look at different pHs. Now, pH 7, an amino acid forms what's known as a zwitterion. Okay. So a zwitterion is basically, I'm going to provide you the exact definition, maybe it'll help it stick in. Zwitterions are known as dipolar ion. They are neutral molecules with a pos and neg charge. So let's take aspartic acid. At pH 7, when it forms a zwitterion, aspartic acid will have a negative charge. Now it loses the H from the carboxyl group always. Its NH2 group gains a H to become positive, and its Z group, remains neutral. Okay, so that's really important. Okay, because it needs to have an overall zero charge. So it doesn't touch the Z group. It starts touching the Z group when you change the pH to extremes. So for example, pH 11, it's got a high concentration of hydroxide, so it's completely deprotonated. That means the COOH will lose its H, the NH3 will not be NH3, it'll lose its H, and its Z group will be deprotonated. Therefore, at that pH, it'll contain a negative charge overall. Now, pH 2, it'll be a high concentration of H plus in solution, so it'll be fully protonated. So it'll look like that. Another thing that you guys have to know is about enzymes, about how they function and what can destroy their function. But the way we can get into the crux of enzymes is by knowing the primary, secondary, and tertiary structure of proteins. So your primary structure of proteins is simply the amide bond between amino acids. Your amide bond is covalent in nature. So this is primary. It talks about the sequence of amino acids and the amide bond between them. Okay, so the primary structure is simply this, the sequence of amino acids, whatever this is, alanine, glycine, etc., and the amide bond between them. Secondary structure talks about hydrogen bonding between NH2 and C double bond O, NH and C double bond O, specifically atoms in the amide bonds in the backbone of the protein. So because every single protein, I'll show you what it looks like. So hydrogen bonding between atoms in the backbone of the protein, hydrogen on the NH and oxygen on the COO is the secondary structure. Now because every protein has amide bonds but also has them a specific distance away, they form, two different proteins may form a similar secondary structure. What I mean by that is if you get insulin, or if you get hemoglobin, or if you get a different type of protein, if they may all have an alpha helix, that alpha helix will be exactly the same proportion in every single protein. It'll have the same bond angles, it'll have a hydrogen bond, then it will be separated by an amino acid, then it will have another hydrogen bond separated by an amino acid, another hydrogen bond, And then every 4 amino acids, that's where the 2 bonding occurs between. This will be the same in every single protein. Whether it forms an alpha helix or a beta pleated sheet is well beyond the scope of the course. And it's determined by other proteins actually that help fold it, as well as, you know, the pH, the environment, the amount of water present, etc. So hydrogen bonding is not specific to the protein when it's between amide bonds. It becomes specific, however, in tertiary structure. So tertiary structure refers to bonding between Z groups. Now, Z groups and the specific sequence of these Z groups is very specific to different proteins, so it's unique to proteins. So, for example, it can be hydrogen bonding between OH and NH, you know, in the amino acids. So I'll show you an example of amino acids which can hydrogen bond. For example, serine can hydrogen bond to glutamine, okay? Ionic interactions. So if there's an NH2 group, let's just say in lysine, let's say that this becomes NH3+, and aspartic acid becomes COO negative, or glutamic acid becomes COO negative. They can bond together, forming an ionic bond. It's also known as a salt bridge. Okay. Then we've got covalent bonds. Covalent bonds only occur between cysteine Z groups. So, oops, that was on the previous page. So cysteine's over here. This can undergo a covalent bond with another cysteine at the Z group. And what happens is it looks like this. So originally they're SH, these H's come off and the S can bond together. This is a covalent bond, it's very strong. And then we can have dispersion force interactions between non-polar Z groups. So that's primary, secondary, and tertiary structure. Now we've really got to make a move on to enzymes. Enzymes are catalysts, they speed up the rate of reaction. They're called biological catalysts because they exist in living things. They work by bonding to a substrate. Now, let's say that the enzyme shape is like so. The substrate shape may be like so. Substrate equals reactant. So the enzyme may act on this particular substrate to split it up into 2 separate products. Okay? The enzyme is regenerated though at the end of the reaction. So there's a few things that you can say. Enzymes, active site, which is the site of activity, which is where the substrate bonds and where the reaction occurs. Enzyme's active site is complementary to substrate. Enzyme's active site is like a lock, and substrate fits like a key. You may also say the enzyme forms specific bonds with the substrate. So enzymes action, sometimes they have a cofactor in there that can form ion dipole bonding. I'm going to show you in a moment. So the substrate is normally held in place by dispersion force interactions, ion dipole interactions, hydrogen bonding, ionic interactions as well. So I'll show you that here. So here we've got a substrate, angiotensin 1, and here we've got the ACE active site, angiotensin converting enzyme. So what it does is it bonds with the substrate. Now here the enzyme's active site is just here. It's the hole in the enzyme, the cavity, which can undergo the specific reaction. Now we've got particular functional groups and also particular functional groups and branches and particular atoms in the angiotensin substrate which form specific bonds with the enzyme's active site. Here 3 of these bonds are shown. Here in the enzyme we've got NH3+, it's forming an ionic bond with angiotensin. Here we've got an NH, it's forming a hydrogen bond with angiotensin. Here we've got a cofactor in the enzyme, which is just zinc. We know that zinc's not present in enzymes, which are protein, but can bond to the cofactor, and it forms an ion dipole bond with the angiotensin. Another thing about enzymes you need to know is that they are very sensitive. They have an optimal pH and they have an optimal temperature in which they can function. And we'll explain why. So, when we change the pH, we risk changes charges on groups. Let's say that these two are bonded together in the enzyme's tertiary structure via an ionic bond. Draw that out better. Okay, we have an ionic bond between them. Now that that is a strong interaction, but if you change the pH, let's say that we decrease pH, we may protonate this group and keep that protonated. These two will no longer be attracted to each other. This means that when you change the pH, you can denature the protein. Now, if you denature the protein or the enzyme, it renders it inactive, as the active site is no longer complementary to the substrate. Now with temperature, if you decrease temperature, you only lower the activity. But does not denature. But if you increase temperature, you increase activity at first, but then you can break H bonds, which again render the enzyme inactive through denaturing it. So they have a specific temperature and pH range that they work optimally at. Okay, so one last biomolecule that we're going to do is DNA. There's not much you have to know about DNA. You just have to know really that the monomer, oops, sorry about that. That the monomer is called a nucleotide. The monomer is made out of three things. I'll show you where to get that from your data book. The monomer is composed of deoxyribose molecule, a base, and a phosphate. So these four are called nitrogenous bases, and this is called a phosphate. So what bonds with what? Well, the NH bonds via a condensation reaction to the deoxyribose there. And then the phosphate, it's easier to think of it as a H there, bonds, oops, we'll do a better colour than that, bonds via a, bonds via a condensation reaction to the deoxyribose there. So the phosphate and the base bond to the deoxyribose. The way my year 10s remember it is the sugar's in the middle. It's like a sugar daddy. It's connected to both of the specific components. So like that, the deoxyribose in the middle, the phosphate in the base, and then represented from your data book here and shown here. Therefore, 2 water molecules are lost when we make a nucleotide, which is just the monomer. Then when we put the monomers together, if we numbered this, we would number this closest to the OH, which is bonded near the ether. So 1, 2, 3, 4, 5. What happens is the 3' OH bonds to the 5' phosphate. Okay, of another deoxyribose molecule. Another nucleotide. So here we've got 2 nucleotides. See, it's got the deoxyribose, the base, and the phosphate. This 3' OH bonds with the phosphate of a different nucleotide, and that's bonding here. This link is called a phosphodiester bond because it looks like 2 esters. Okay, we then have secondary structure of DNA. DNA exists as a double-stranded helix, which is antiparallel, and A pairs with T and C pairs with G, the curved ones together, or gangsters can ask time. Adenine pairs with thymine with 2 hydrogen bonds. The way it's represented in the data book is like so. This adenine pairs with this thymine. The 2 upper groups are bonding, and the bottom group in thymine is limited by the fact that adenine only has a CH there, and guanine bonds via 3 hydrogen bonds with cytosine. So we'll show that here. These are where the bonds occur. And that's pretty much it for DNA. Now we're going to jump straight into questions. So if you guys grab the worksheet that was, in the same folder as the video link, you can grab this worksheet and you can answer along with me. So we're just going to go quite briskly through the questions. You can pause it at any time and go through the question yourself. I would actually suggest you do that and then see how I answer it if you still need that help. Okay, so here we're going to question 16, 2011. So here we have a starch molecule. It contains 500 glucose units. Remember that starch is the way plants store their glucose in a polymer. It's represented in the same way as glycogen, so with the CH2 OHs all pointing in the same direction, but it's less branched. Regardless, starch is made of 500 units, so you can imagine 500 monomers together. So the molar mass of glucose is 180 grams per mole. The monomer. But they want to know the molar mass of starch. You've got to remember that every time you connect two monomers together, you get the loss of one water molecule. Okay? It's in the condensation reaction. So if we join two monomers together, we get the loss of one water molecule. Three monomers together, we get the loss of two water molecules, etc. 500 monomers together, we get the loss of 499 H2O molecules. So if we want to work out the molar mass of starch, it's going to be 500 times 180 for the glucose molecules minus 499 times 18 for the loss of waters. So if we just calculate that, it is 8982 and 90,000 minus 8982 equals B. Okay, moving on to question C. The enzyme trypsin catalyzes the breaking of peptide bonds in proteins. Trypsin is active in the alpha part. The pH is between. Okay, so in this question, it's saying, sorry, 1 second. In this question, it's saying we've got an enzyme called trypsin. It breaks peptide bonds in proteins. So that would be its substrate, the peptide bonds in proteins. It's active in the upper part of the small intestine where the pH, so this is specific to its, this is the optimal pH. Okay, trypsin is not effective in the stomach where the pH is 4. So this is going outside of the range of the optimal pH. It wants you to suggest a reason why. Now for this type of question, you need to say why it's not effective. So why it actually loses its activity. So we learned that there are two ways or two main ways that you need to know why enzymes lose their activity, and that is an increase in temperature or a change in pH, so non-directional. So if we answer this question, you need to be specific to pH. So you may want to pause it and try to answer. Okay. you need to say the active site will lose its shape / denature, but that's not sufficient because you haven't connected it with structure, and in chem it's all about structure. So it will lose its it'll lose its shape / denature because a decrease in pH protonates, adds protons to parts of the protein that were previously deprotonated. Okay, so here we've got the next question. Question 6, 2011. So lysine, alanine, and aspartic acids are all amino acids. Now they want you to say which one of the following will react with HCl. Well, we kind of went through this exact example when we were talking about it, but you need to know that all of them, in fact, will react with HCl because they're all amino acids, okay? And they all have the NH2 group, which is basic. So this question's quite difficult. This is question 3, I'm guessing 2011 as well. So in this question, they're asking you to, sorry, there's one more. So in this question, they're asking you to have a look at 2 different types of polymers. How can I tell they're polymers? Because they have these open-ended covalent bonds. This is the way you draw a polymer, guys. If you draw the bracket and the ... you're showing that this component is repeated over and over. In nylon it is, but I mean the easiest way to do it is with the open-ended covalent bonds. Now we've got nylon, we've got protein. It says nylon is composed of 2 monomers. The structure of one of the monomers is shown below. Draw the structure of the other monomer. So if you have a look at that, nylon, the way you can tell what a monomer is you've got to ask yourself the 2 questions. Is it formed by a condensation, polymerization, or is it formed by an addition, polymerization? Now the way that's going to be really obvious is in addition you'll only have carbons in your backbone because it occurs between a carbon-to-carbon double bond. In condensation you'll have other elements. So here it's condensation. We have definite amide bonds. So you have to ask yourself, after you know it's condensation, you need to ask yourself what type of bonds, and that will give you the functional group which formed the bonds. We know in amide bonds it was formed by an NH2 group and a COOH group. Okay, so it says nylons are composed of 2 monomers, so the COOH group is represented here and the NH2 group is represented there. So the other one should look like this. Okay, and it says here, name the functional groups that link the monomers together. Well, it's amide and amide. For this protein, you could have said peptide as well, but if you said peptide for nylon, you'd be wrong, because remember, it can only be between amino acids. Okay, question 6. Enzymes are a complex protein structures that function as biological catalysts. Why does a particular enzyme generally only catalyze a specific reaction? Now this particular question is taken from the PowerPoint, so we're going to go through the answers on the PowerPoint for enzymes. Okay, so why does a particular enzyme generally only catalyze a specific reaction? You have to say something about its active site being complementary to the substrate, or it making specific bonds with the substrate. So those sentences that we wrote down before. But this is what VCAR accepted for that. Enzyme's function is determined by the shape of the active site. The enzyme shape is complementary to a specific substrate. Lock and key effect. The substrate reactant is the key and the enzyme's active site is the lock. An enzyme's active site has a shape allowing access to only particular molecules. Invertase is an enzyme which catalyzes the conversions of sucrose to fructose. Okay, and we have to determine at which pH it has the maximum activity. So if you have a look, it's got all these different lines because they're at different temperatures. As you can see, when we change the temperature, we change the activity. But you can see this would be the optimal pH, it would be 5. Now the optimal temperature is where you have the maximum activity, and in this case it's the triangle, so it's at 55. Why does changing the pH? Well, we've spoken about this before, but I'll read you another VCAR response. The tertiary structure changes with a change in pH. The change in pH plus concentration when we change the charge on side chain group. The enzyme is denatured, so the shape of the active site changes. So either one of those. Okay, I really wanted to just do this zwitterine one. This one, name the amino acid that makes up a section of the polymers. So that's serine. You just look up your data book. This is glutamic acid, and this is glycine in glutamic acid again. So it says here, choose one of the amino acids in this section and draw the structure as a zwitterine. So we'll choose glutamic acid because it would be sort of, or we'll choose serine. Whoops. Remember the Z group, when it's a zwitterine, it has a charge of 0. So the Z group should remain protonated. Not that it would change in serine, but it is the carboxyl group which gains a negative charge, and the amino group which becomes the conjugate acid gaining the positive charge. Okay, and then yeah, for glutamic acid, you have your COOH group, which remains the same if it's in the Z group, and you'd have your protonated and deprotonated groups on the ends. So they both have a charge of 0. Of course, you only have to put 1. So draw the structure showing all bonds of the amino acid serine as it would exist at pH 2. Now, first you've got to look at serine. You've got to look, does serine have any amino groups or carboxyl groups? Well, yes, it has it just like every other amino acid, but it doesn't in its Z group, so the Z group stays the same. Now, pH 2, we have a concentration of H+, which is high. That means everything would be maximum protonated. And we have an NH3 group, which is protonated as well. Name the functional group on the side chain of serine. Well, it's a hydroxyl group. Write the molecular formula of phenylalanine. Okay, so the way we can tell, I mean, we've got a skeletal formula, so it can be quite difficult, but you count the number of C's. Each tip here is a C. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 carbons. For the H's, because these are double bonds alternating, you need to make sure you don't count that as a H. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oops. O, 1, 2, N. Okay, so C9, H11, O2, N. Just want to know what section of the state got that. 29% got that. Response to this question displayed a number of consistent errors, including having 12 H's in the molecular formula, probably because students did not recognize that for the carbon atom on the CH2, benzene substitutes for a H atom, converting C6H6 to C6H5, leaving out N, providing a semi-structural formula rather than a molecular formula. Two different dipeptides can form between. We're going to come back to that because we're going to do it in another question. Okay, question 8. A biomolecule is chemically analyzed and found to contain only the elements carbon, hydrogen, and oxygen, nitrogen, and phosphorus. What is this one from? Oh, 8 as well. C, H, O, N, and P. Well, that gives it away that it's DNA. The second one, so, nicely positioned there. So, a piece of double-stranded DNA. This one got a lot of the state. So, when it's double-stranded DNA, we're talking about when it's hydrogen bonded to its partners. So, when it says a piece of double-stranded DNA, which has 200 base pairs in length, it's actually got 400 bases. Okay? If it contains 50 T's, it means that it contains 50 A's. That adds up to 100, meaning that we've got 300 left, meaning that it has to have 150 G's and 150 C's. So the number of G's is 150, so it's D. So 63% of the state got that. Okay, now we've got some sort of a few more difficult questions. Okay, what is the mass of 1 molecule of deoxyribose? Okay, now I asked this type of question a little while ago, but anyway, if you have a look at it, it's asking for mass. So it's asking for little m of deoxy equals question mark. You should always summarize exactly what the question's asking you. Now what the question is telling you is we've got 1 molecule. So capital N of deoxy equals 1. So you need to go from N being 1 to mass. So we know that N equals N over Na. That's the first thing that we're going to do. 1 divided by Avogadro's number. We are then going to do mass equals moles times molar mass equals 1 over Avogadro's number times the molar mass of deoxyribose. Now what's the molar mass of deoxyribose? 1, 2, 3, 4, 5. 134 divided by okay, I don't have my calculator on me. We've got the answer here. Hopefully we've got the same working out. So 134, yep. So 2.23 times 10 to the negative 22, which is B. Okay, this one was just because it was attached there, but it's not related to biomolecules. So this question says that glycine and alanine. So glycine has a Z group just with a H, and then alanine has a Z group with a CH3. Can react together to form two different compound dipeptides. So dipeptides are when two amino acids are bonded together. Okay, so it wants you to draw two possible dipeptides. Now you need to draw them both. Now the only two possibilities are if you've got you have the amine group of glycine reacting with the carboxyl group of alanine The other possibility is if you actually had alanine first and glycine last. Oops, nearly stuffed that one up. So like so. Okay, so this question. Just to dwell on this just a little longer, when there are two amino acids, there are two possible dipeptides. But when there are three amino acids, let's just call them A, B, C, it actually increases the number by quite a few. So it's all based on, it's mathematically related. You can actually make 6 different dipeptides. Hopefully VCard doesn't get you to do that. Okay, now this question was something that was answered quite poorly on the exam actually. And it says PLGA, so it's a biodegradable polymer. It's used in the production of biomedical devices, blah, 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 blah. But basically it wants you to discern the monomers. Now, in discerning the monomers, you really need to look at whether it was polymerization from addition polymerization, that is, it only has carbon in its backbone, or if it was condensation. Now, straight away, it's got oxygen in its backbone, so it was condensation. And then you look at the link. Now, the link that is linking the monomers together is an ester link. And we know that that gives us the functional groups because we know an ester link is made out of a carboxyl and a hydroxyl. So all you've got to do, because it was originally formed by a condensation reaction, all you've got to do is break it and add water to each of the bonds. Okay, so straight away you can see that this is going to be one monomer. So one monomer is going to have a CH to a CH3 and an OH. So it can't be this. Could be this. Can't be that. Okay. And the other monomer, and it's of course going to have a COOH on the other side, yep. And the other monomer is going to have CH2 and OH on one side, and then a COOH on the other side. So CH2, OH on one side. Looks like it's A to me, but let's just check this one. CH2 doesn't have an OH, so it can't give D. Okay, this one we've done before. We're going to go to this one. Actually, we're going to skip that for a second and we're going to go to this one. It's a little easier. Which of the following will have the highest melting points? Now, this is a really good question. It shows you it nice and, obviously the way it's shown you, because it's showing you the positions of the double bonds. Now, this double bond has created a kink in the chain. This one has two double bonds, which has created a greater kink in the chain, and this one also has two. So, although, and we've got to see this one, we've just got to see if it is saturated or unsaturated, because they haven't given it to us in this perfect arrangement. So, it would be C, we've got to put it in that formula, so C22, but C23. H 44, 47. So 23 times 2 plus 1, this is saturated. So this should have the highest melting temperature, because even if you count the number of C's to see if dispersion forces will be higher. 1, 2, 3. 22, it's still, it's got a relatively the same number of C's. So if you just have a look at what they have, correct answer is A. Having carbon-to-carbon double bonds causes a chain to align more irregularly and therefore reduces dispersion forces. Okay. So we've got this question. It's quite a common question, and it's to determine how many double bonds we've got. Now, whenever you've got a double bond in your fatty acid chain, this could react with a number of things. It could react with H2, I2, Br2, Cl2. It could react with F2. It could react with H2O. It could react with lots of things, depending on the type of catalyst, etc. But we can use a mole ratio between the double bond and our reactant to determine how many double bonds we've got. If we've got one double bond, it'll be one bromine or whatever it is. It'll be a 1-to-1 ratio. But if we've got two double bonds, it's going to require two bromines. So it'll be a 2-to-1 ratio. So it's 1 mole of bromine to 1 mole of double bond. If you've got 2 moles of double bond, you need 2 moles of bromine. So that in mind, it says 0.01 mole of the fatty acid. So that's the mole ratio of the fatty acid. Requires 7.61 grams of iodine. Identify the fatty acid and write a balance equation for the production of methyl ester biodiesel from this fatty acid. Okay, so if we have a look, it says we've got 0.01 mole of the fatty acid, And the amount of moles of iodine that requires to react with it, well, we have to work that out. Zero point 0.03 mole. So it must have 3 double bonds. And if you have a look here, I2 reacts in an addition reaction across the carbon-to-carbon double bond. It has 3 double bonds because it's got 6 less H, therefore it has 6 less H atoms than the saturated fatty acids. Okay. The rest of the question says, identify the fatty acid I just don't think there is enough information to answer this question. Let's have a look at the original question. So what you need to do is answer a few more questions on biomolecules, possibly VCAR questions on biomolecules. Make sure you've got it down packed. Come and see me if you don't understand it.